My TTL computer, update revision 2B, first program running, executing subroutine calls. So it's just a simple program that's outputting 1 to the display and then makes a function call to a subroutine that's outputting 2 to the display. That's returning and then just looping back to the beginning of the program. So we're just seeing 1 and 2 displayed on the digits display. But hey, here we have a executing program with pretty sophisticated microcode implementing the call and the return, and also implementing the stack. So pretty cool, pretty complex microcode running on the computer. One thing more I want to do update is that we need a scratch register is needed to keep a temporary store of the function call, of the function address rather, in the call statement. It's using the A register, so that's corrupting both the A and the B register when you make the call. So we really don't want that. I want to be able to preserve the A register because we want to use the A register to be able to pass a single argument to the subroutines. So what I'm going to have to do is update the ALU code to implement another scratch register, a Y register, and we have to put in read and write ability to that scratch register, and that's what will be used by the microcode. So I'll have to do update the ALU, and then I'll have to update the control unit microcode to use that scratch register rather than A. And then we'll really have a solid revision 2 version of the hardware, and that'll all be set to implement the serial I/O functionality. And to use that serial I/O functionality, right, we're going to basically want to be able to implement the terminal through that, and we also want to first thing I'm going to do is write a little bootloader so we can key in the bootloader, and then we can load more complicated program using the bootloader and the terminal. So that's my main objective, and we'll be able to do some longer programs. And then once that's all done and functional, I'm actually going to write a small assembler so I can code this in the editor on my laptop, be able to assemble that into a hex file of sorts, then using the bootloader, load that program into memory. So at that point, we'll be able to do more sophisticated programs, to be able to do something kind of interesting little games that way. And that's kind of our goal. So yeah, a lot of good work had to happen to get to this point. And one thing is that when I went through writing the microcode, I did not have enough steps in the microcode to implement the call, instruction, because we only had eight steps, instruction steps. So I had to increase that to 10 from 8. So we now use a 4-bit instruction step counter, and I also had to put in logic to be able to reset that counter, because it's actually counting up to 15, but we only need to use a maximum of 10, and we don't want to waste all those cycles. But so now inside the microcode, each step can reset the counter at any point in the microcode. So that really is going to have the effect of really speeding up the execution, because each instruction was taking 8 instruction ticks. Now, because of the reset, most of them are only going to take 4. So the effect of that is going to be a speed up in the program executions, and that will be a good thing, and we'll need those clock cycles. So hey, very good update to this point. Things are looking really, really good. I only have a really slow clock running right now, but if I do bump this up to the super fast speed, you can see that the whole system holds together and it's looking pretty solid with all the hardware updates that we've made to stabilize the system. Anyway, looking really good. Really pleased and happy that I was able to get this far and that things are looking pretty good, and really awesome to have implemented the stack and the call and return. Pretty neat to do that. Anyway, thanks for watching.